Hi, welcome back. I'm super excited about this video because this is the introduction I wish I had had as a mechanical engineer into how finite element analysis works. And I really feel like knowing what's going on behind the scenes will help anyone who's working with the finite element method to troubleshoot their errors and to do high quality work. So if you've got questions about what's happening under the hood in your finite element software, no matter which one, because they all work the same, then you came to the right place. Let's get started. All right, I'm calling this presentation the FEM behind the FEA. FEM standing for finite element method and FEA standing for finite element analysis. And of course, this is just an intro. Let's get started. If you have a long piece of rubber, let's say a rubber band that you cut open, right? And it has some original length, and if you apply a stretching force to it, it's going to stretch, right? So we're going to call that original length L, and we're going to call the force F, and we're going to call that change in length the delta L. Now, let's say you have a rubber band, but it's much thicker this time. It has the same original length, and we apply the same force, but the delta L is going to be smaller, and we know this intuitively. The thicker it is, the harder it will be to stretch, right? So what changed? This is the cross-sectional area, a very important aspect of any material we're analyzing, right? If you cut a thicker rubber band and measure the area of that slice where you cut, it's going to have a larger area. So that's why we call it the cross-sectional area. Now let's say you take that original rubber band and replace it with a nail. It has the same original length, and you apply the same force, but we know that it's not going to stretch, right? If you're doing this with your hands, you won't be able to notice how much it stretches by because it's so minuscule. Its delta L is tiny. The difference between the two is an inherent difference in the materials themselves. This is what we call the elastic modulus, and we denote that with the letter E. This can also be called the Young's modulus. And this comes from the molecular structure of the materials themselves. The carbon and iron atoms in the steel are going to hold on to each other tighter than the carbon and hydrogen and oxygen in the rubber band. And to describe the elastic modulus, essentially what we do is we plot how hard we pull and how far it stretches, and we experimentally do this and look at the curve that arises from it. And so this is what one for rubber might look like. And if we look at one for steel, it's going to be very straight, very linear, at least until it starts to break down. And it's going to be much steeper. So that slope of the curve, that's what we call the Young's modulus. And this is an oversimplification, but I'll have more on that later. So now we have everything we need for the finite element method. We have force, we have the original length, we have the elastic modulus, we have the cross-sectional area, so that way we can find the change in length. This is all we need to measure and predict how a material is going to behave under certain forces and stresses. You could also say that the Poisson's ratio is very important for this, but that more comes into play in 2D and 3D, and so we won't worry about that for now. So if we put it all into one equation, we have delta L equals FL over EA. Force F and our original length are on the top in the numerator because the higher your force or the higher your original length, the easier it will be to get it to stretch. And the E and A are on the denominator because the higher those values are, the harder it will be for the material to stretch. And this should feel pretty intuitive. We can move this equation around a little bit. F over A, we can call that stress and denote that with sigma. And if we look at delta L over L, we can call that strain, kind of a normalized measure of how much it stretches by. And this is where our stress equals E times strain equation comes from, which is very important, and hopefully you recognize this from mechanics of materials or really any engineering class. And I should say that when I mentioned the pulling force versus length stretched curve earlier, really we're looking at stress and strain because these are normalized versions of the force and the stretch amount. So they account for varying cross-sectional areas and varying original lengths of the materials themselves. So another way to use the same equation, if we move it around, we can put force all by itself on the left-hand side. And if we take this EA over L section and we just give it a different name, we kind of lump it all into one, we call it K, then we get this equation, F equals K delta L. And I hope this is kind of ringing a bell. I want you to look into this man's deep blue eyes, because this is Robert Hooke, and this is Robert Hooke's law. You know, from physics 1 with the springs, this is the spring equation. And so if we take this equation, EA delta L over L, then we can take any material for E, its weird cross-sectional area with A, and we can represent its weird original length with L. So this might be of an engine or of a bone, like really complex shapes, really complex materials, and we can take that and we can reduce it into a very simple equation where it all behaves and is modeled as simple linear springs. Okay, it might be behaved as a network of linear springs, but that's okay. We can work with that. We have linear algebra to take care of that, so we're not concerned. So here's how it works. First, we're going to do our pre-processing. In pre-processing, we're going to slice the part into pieces. So here on the right, you can see my femur, and it is all broken up into elements, which are the area, or in 3D, the volume components, and it is broken up into nodes, which is where those intersect. The next step is element formulation. In this step, we're going to apply this equation we just talked about to each element. We're going to take the unique material properties, cross-sectional area, and original length of each element and convert it into its own little spring equation all over the whole material. And then we're going to add boundary conditions as well. So boundary conditions might be, okay, these nodes at the bottom of the femur, we're going to say those are fixed. Or we might say the nodes at the top have a force applied to them in a certain direction, or that the nodes on the side, maybe these can only move in a certain direction or something like that. So these are examples of boundary conditions that we would apply during element formulation. Then we have assembly, where we're going to take all of those equations that we just made for each element and we're going to put them into one matrix equation. We're going to have a vector of force values, a matrix that represents our stiffness or K values, and we're going to have a U vector which represents our displacements of each node. While this isn't exactly the change in length, the displacement can be used to find the change in length, and so it just works out to be much simpler to use displacements at this step as opposed to going straight for the change in length. So this is what our force vector looks like. This is what our K vector looks like. This is what our displacement vector looks like. So each node has a number, each element has a number. And so the F1 value here is all the forces that act on node 1. And F2 is all the forces that act on node 2. And similarly, our K1 value is the stiffness of element 1. And our K2 is the stiffness of element 2. And then in our displacement vector, this represents the displacement of node 1, U2 represents the displacement of node 2, and so on. Once we have that all figured out, then we can solve the inverse problem. Here, we're going to solve for displacements. Using displacement, we can find whatever values we need. So we just need to find the inverse of K and multiply that by F to find our displacements. From there, we can post-process. We can extract all the juicy information that we want to report on or understand about this material or this design or whatever it may be. So let's work through a simple example. When I was in high school, I had these shoes that I loved. They were cross-country shoes, the Saucony Kilkennies, in exactly this blue and orange color scheme. I thought they were awesome. And on the bottom were spikes to help me run faster and grip different terrains, right? They were pretty sharp. And you'll notice that this one is missing. And that's probably because these spikes also fell apart. I mean, they got destroyed if during a race we had to run on asphalt or on concrete or anything like that. They always were getting bent and twisted and just super beat up. So I want to understand why. Let's take a simplified model. I did reduce the diameter and the length and just turn them into similar values, but ones that will be easy for the math. So in this case, we're going to say the left side is fixed, and we're going to say a force of 1800 newtons is applied to the tip. And this force represents if all my body weight with a little extra because I'm accelerating were to land directly onto one spike. So let's do our pre-processing. We're going to break this up into elements and nodes. So we'll break it up into 4 nodes, and that makes 3 elements. And we're going to make all these elements the same length just for simplicity's sake. And basically our pre-processing is done. In more complex or multidimensional examples, this is definitely not a trivial task, but here it's pretty straightforward. So let's move on to element formulation. We're going to take our F equals EA delta L over L equation, and we're going to apply it to each element. We're after our K matrix here, right? So let's look at just the first element. It has an original length of 2 millimeters, because 1/3 of 6 millimeters is 2. And so our original length, check. Young's modulus, or elastic modulus of steel, that's pretty easy to look up. It's about 200 gigapascals is a pretty good estimate there. So E, check. So all we need is A. If we look at the left, we have a diameter of 2 millimeters. And if we look at the right, we have a diameter of 2/3 millimeters. And so this is kind of a tricky spot, because if we use the diameter on the left side to calculate our area, that's going to overestimate the strength, because it's going to overestimate the cross-sectional area. If we use the value on the right, then that's going to be too weak. So we should be somewhere in the middle. But again, to make the math easy, we're just going to do the too strong example. So with a little bit of geometry, it's pretty straightforward to find that cross-sectional area. So boom, we have everything we need to know the K, or the stiffness value of that first element. So we need to do this with all of our elements, right? So these are our diameters and their corresponding areas. So let's put them all together. Our first stiffness value is going to be that first Young's modulus times the first area over that first length. But remember, these are all made of the same material and they're all the same length. So we're just going to simplify this to be K1 equals EA1 over L, E and A being the same across all. So there we go. We just need to put in our A2 and our A3 there. And now we can really put them all into our stiffness matrix. Our stiffness matrix looks like this. If you want to know why it looks like that, then let me know and I can make another video. But we're just going to plug these values in for now. So our EA1 over L goes here. Our EA1 plus EA2 over L goes here. EA2 plus EA3 over L, EA3 over L, it's right. And then everywhere not on the diagonal or next to the diagonal is going to be 0. So that's pretty easy, honestly. These stiffness matrices can become really big because it's going to be the number of nodes by number of nodes in dimension. So plugging these values in, we have these values, and I pulled out a 1000 just so that it would look nice here in the matrix. You have to be really careful with your units here to make sure that they line up. So we have our K. Let's move on and look at our forces. On the right, we have a 1800 Newton force. If we look at our coordinate system here, then we can see that since positive x is running in the right direction, then this is going to be a negative force. We also have a reaction because these nodes are fixed, and so there needs to be an equal and opposite reaction force. So if we move this to our simplified diagram, then there's a reaction force on node 1 and a force on node, this is supposed to be node 4. So plugging that into our F vector, we have R for reaction in node 1 space, and then we have 0 and 0 because there's no forces acting on node 2 or node 3, and a negative 1800 Newton force on node 4. So our F vector is ready to go. Now let's find U. On the left-hand side, we know this one isn't going to move because it's fixed. So we can put a 0 in for U1. And the rest of these, I don't know. That's actually exactly what we're solving for. So if you think I was just going to plug these in, then you're a silly goose. With that, we're just going to leave these as variables, and we're going to solve for those. So our U vector is finished. Let's move on and solve. We're going to take our F equals KU equation, which, by the way, looks like this. We have our F equals K times U. And so now we need K inverse times F to give us U. We have an unknown on the left-hand side and 3 unknowns on the right-hand side. And so that becomes very hard to solve. So what we're going to do is partition the matrix. Basically, we're going to cross out all the values associated with the unknown in the left-hand side and basically solve everything else. I promise this is real. Look it up. I didn't believe it was real when I first learned this, but it totally is, so that's pretty sweet. This is what our equation looks like now with our reduced F equals KU vectors and matrix. So if we invert the K matrix and multiply by F, we can get U, and you can use whatever solver you want to do for that. And basically, drumroll please, our U vector equals negative 0.0057, negative 0.0572, and negative 0.2572 millimeters. So there's our final displacements. Let's move on to post-processing to kind of understand what these mean. Let's take this value, this displacement of the 4th node, and we're going to look at our original model, so with an original length of 6 millimeters. And now if we apply that displacement on the end, that puts our final length to 5.744. You know, a displacement of 1/4 millimeter when it's only 6 millimeters long is pretty substantial. Now if we take our elements and break them up and apply our stress equals E epsilon equation, then using the areas of each element, we can calculate our stress to be these values. And I want you to notice that in element 3, we're looking at over 20 gigapascals, not even megapascals. And when you consider a typical yield strength for steel to be 700 megapascals, we're way over that, which explains pretty well why these shoes always had torn up and totally shredded spikes after I would run on them. Now, there's a lot that I didn't go over in this video that really could have. I mean, there's a lot of bells and whistles that go into making finite element analysis both mathematically and practically robust, you know, in multiple dimensions and across different domains. I'm still learning a lot of those. But like I said, this is the introduction that I wish that I had had. It's a great starting point, in my opinion, for starting to understand all the different things that go into good finite element analysis. So I hope it was helpful. Thank you so much for watching, and I'll see you next time.